flow, that is an example of buoyancy driven flow. Okay, when we go to boundary layers, we will discuss natural convection boundary layers as well. So these are the very standard examples of boundary buoyancy driven flows. And so we were saying that what happens in these buoyancy driven flows, what are the governing equations. So we had formulated from del rho by del t plus del dot rho u equals 0. So we had derived from here the non-dimensional equations for rho prime star, and there was a u star as well, right? So we had a u star, okay, which was nothing but u by capital U, where this capital U we had derived is delta rho over rho GL. Okay, this was what we had derived. So we had derived a correct scaling of this velocity, and this is what we had obtained. And if we substitute these things here, we got that at order 1 we have del star dot u star 0, and at order epsilon we had del rho prime star over del t star plus u star dot equals 0. Okay, so these were the two equations that we had obtained from the density equation by considering order 1 and order epsilon separately. Okay, and what you should see from here is that this equation in fluid mechanics, this equation is usually called a simple convection equation. Okay, the idea of this equation is that, so what is this equation? This is essentially saying that d by dt star of rho prime star is 0. Okay, which means that if there is a fluid particle, okay, the fluid particle's density doesn't change. As the fluid particle travels, its density doesn't change. At a given spatial location, the density will change according to this and their balance, but a fluid particle's density doesn't change. So it's saying that the Lagrangian derivative or material derivative of the density perturbation is 0. Okay, so you expect this to happen when you, let us say, have this kind of a situation, and let us say this guy is heavier, this guy is lighter. You expect these guys to maintain their density and just move around. Okay, forget about how these density changes are happening, because that has an important connotation if this guy is going to be 0 or not, as we will see in a few minutes. Because if the density changes are happening due to temperature, then you will see that there is an additional term that is required on the right hand side. Okay, so we'll get there soon. But as far as this part is concerned, as long as there is density differences, okay, and those density differences are governed by this equation, and there is velocity that is due to only convection, then we see that density perturbations are simply convected along the streamlines. This is what that equation is telling. So from the momentum equation we had derived that at order 1 we had obtained, from the momentum equation we had obtained an equation for p bar star, and that was that this quantity equals, this was equal to rho star g star. Okay, this is what we had obtained from momentum equation at order 1. Okay, so this should be very intuitive for you, because velocity is naturally scaled by square root of epsilon. So this is square root of epsilon times GL. Okay, the leading order term of velocity is of order square root epsilon. There is no order 1 velocity in the system. There is no order 1 velocity in the system, because order 1, if you look at order 1 dynamics or statics of this flow, order 1 is simply hydrostatics. At order 1 you simply get hydrostatics. Only at higher orders we start to see that there is some flow that is happening. Okay.
So what does order epsilon mean?
Huh?
I understand what
Order epsilon is, so epsilon was defined as this.
I mean dimension is
Yeah. So the idea is that let us say in a flow you have density fluctuations. Yeah, this is delta rho by rho naught. So let us say in a flow you have density fluctuations which are at max 1% of the base density rho naught. Okay, then order epsilon means that any quantity that you are looking at, if that non-dimensional quantity you say is order epsilon, then it will be 0.01, order 0.01. If it's an order square root epsilon quantity, then it will be 0.1, order 0.1. Okay, that is in a flow that has density fluctuations of at max 1%, you cannot have velocity which is, let us say, 1 times square root GL. You cannot have that kind of velocity. Okay, that is what this order means. This order is telling you, okay, but at what decimal units you need to expect some numbers to measure the quantity. Okay, if I tell you that you have this as the order of velocity, that is, I am telling you order of u star is square root epsilon. Okay, then let us say a flow has 1% density fluctuations at max. Then I am saying that order of u star is 0.1. Okay, what does u star 0.1 means? That means this velocity, order of velocity will be 0.1 times some square root GL.
so u star will be 1 by root epsilon.
No, u star is what square root epsilon.
Capital U is proportional to root epsilon. So
Oh yeah, my bad. Yes, you're right. Hold on. Just a second. Yes, you're right. Not 1 by epsilon. So the idea is that order of, so if 1% density fluctuations you have, then order of this velocity scale is square root epsilon, so that is 0.1. Okay, that is order of velocity scale is 0.1 meters per second. Okay, or to be exact, this is order epsilon times square root GL. So whatever length scales you are looking at those length scales you have to consider the square root GL and then multiply it with square root epsilon, and that gives you an order of magnitude of this velocity. So this gives us an order of magnitude of the velocity scale in the flow. When I say it's square root epsilon, it's telling me, okay, what kind of velocities do I need to expect? Let us say over 100 kilometer distance, I have a density fluctuation of 1%. Then what is the velocity that I am expecting? Is it going to be 100 meters per second, 1 meters per second? What kind of velocity should I expect? Okay, that is the answer that you can get from this kind of scaling analysis. The order of magnitude analysis, which I don't know, was it covered in APL 106? Huh? Order of magnitude analysis, boundary layers or something. Huh? It's been covered? No, one guy is saying covered, one guy rest. It's becoming very difficult to take advanced courses at IIT Delhi, you know. I don't know what is going on in your foundational courses. I guess everyone is interested in finance. So usually in APL 106 or the first course in fluid mechanics, we introduce order of magnitude analysis when we go to boundary layers. Very rudimentary discussion of boundary layer theory. When we do, the order of magnitude analysis is introduced. Okay. So you should go back and take a look at the notes, or you can look at your undergraduate the first course textbooks, Frank M. White and Fox McDonald, whichever one was followed. You can look at those textbooks. It's there as well. It's not like I'm making these things up. Okay, this is supposed to be covered in introductory fluid mechanics courses. Anyway, so this is what we have at order 1 in the momentum equation, and at order epsilon we had derived that we have del u star over del t star plus this guy equals minus grad star p prime star plus 1 by re del star square u star plus a rho prime star g star. Actually there I think what we had obtained was simply this, because rho star we have to take at the at order 1, which is simply 1. That is the equation that will get.
So epsilon is del rho by rho naught, right?
Yeah.
So there in velocity, you have replaced del rho by rho
Yeah,
naught.
that should be del rho by rho naught. Thanks. So these kind of systems are governed by the equations. If you want to look at the flow in this kind of system, given that you have delta rho by rho naught much less than 1, given that this holds, then the equations are del star dot u star equals 0, then the momentum equation and then the density equation. Where? No, that's the thing. No, so I had rho star, that was a mistake, because rho star is also will also be considered at order 1. Just go to your momentum equation and substitute this for rho star. You have 1 plus epsilon rho prime star. At order 1, rho star is 1. At order 1, rho star is 1 because of the definition of rho star and how we are taking rho to be 1 plus rho prime. Rho is rho naught plus rho prime, not 1 plus rho prime. So rho star is rho by rho naught, and that's how I define it. So these are your governing equations. If you notice that compared to your standard incompressible flow equations, where you just have velocity and pressure as unknowns, you have velocity, pressure and the density perturbations as unknown. So that's why you have obtained an additional equation. Okay, you have obtained an additional equation. Yeah.
In the second equation, shouldn't it be del star p prime star? Second governing equation.
Yes. Thank you. And now what you can do is, in this course what we are going to do is a lot of times we are going to say, we are going to use the words drop the stars, okay, just so that it is easier to write down. Okay, it's very cumbersome to every time take a note that there is a star at the superscript for non-dimensional quantities. We will say drop stars for non-dimensional quantities, okay, just to make writing easier for us. Okay, there is no other meaning here. The other thing that you can do is, instead of dropping the stars, you can convert these equations back to dimensional form. Okay, using the definitions of these starred quantities, you can obtain the dimensional form of the equations. Okay, you can obtain the dimensional form of equations back. Now, in all of this discussion, what we have actually done is, we have ignored any diffusion of density. Okay, we have ignored, in all of this discussion, we have ignored any diffusion of density. Okay, why would density diffuse? How come there will be a diffusion of density ever? Let us say you have a fluid where this is a hot spot. Okay, here the temperature is much higher than the surrounding fluid. okay, then you expect that the density here will be much lesser than the surrounding fluid, but we know that temperature diffuses. We know that the temperature diffuses, right? We know that at time 0, if this is what we have, let us say this is Th, this is Tc, then we know that at later times we may have a scenario where you have some intermediate temperature of this in this fluid which is somewhere between Th and Tc. Okay, so initially you have a low density, you have a high density inside this region and high density around it. At T tends to infinity, you will have a uniform density. So you can look at this temperature diffusion as density diffusion. You can look at this temperature diffusion as density diffusion. Okay, given that density changes with temperature, given that density is changing with temperature, you can look at it as density diffusion. There is another scenario where you can have density diffusion. Let us say you have you have a fluid and you have another fluid in between. Let us say this is hydrogen, this is carbon dioxide. Okay, if you have a, let us say if you have a small blob of carbon dioxide and hydrogen, ignore any flow that could happen. There will be mass diffusion, there will be mass diffusion, and sooner you will have, let us say this is at t equal to 0, at some t tends to infinity, you will have a blob which is a mixture of this hydrogen and carbon dioxide where their mole fractions are equal, are balanced, homogeneous. Okay, this is basically mass diffusion. We have ignored these kind of diffusions so far in our analysis. Okay, we have ignored this kind of diffusion so far in our analysis, and the impact of this diffusion is actually to have a diffusion velocity. There is a diffusion velocity concept where what you do is there is a velocity due to the flow, but the total velocity you say is this flow velocity plus some diffusion velocity. Okay, and this flow velocity is what we have been considering so far. There is a diffusion velocity that we have been neglecting, and that diffusion velocity, why is that diffusion velocity even there? Why is there a velocity which is not really a flow velocity but still a velocity? And the answer to that is, if you remember in our derivation, we had said that everywhere this u that is appearing, it is the velocity of the center of mass of a fluid particle. Let us say you have a fluid particle which has some density gradient. You have a density gradient in the fluid particle, so there is higher density here, there is lower density here. Okay, as in the fluid particle this density diffuses, then higher density will come on this side. What do you expect to happen to the center of mass of this fluid particle? It will move leftwards. That will introduce this diffusion velocity. It is the velocity of the center of mass. There is no flow happening, the fluid particle is at rest, yet the center of mass has shifted. This shift in center of mass has happened because there has been a gradient of density which diffused. If there was no diffusion, there won't be any shift in center of mass, there won't be any Vd. Okay, now this diffusion velocity is important when we consider a very standard case of Boussinesq approximation where this density change is happening due to temperature changes. Okay, these density changes are happening due to temperature changes. All of this analysis holds, but we have to also account for temperature equation. Okay, we have to also account for temperature equation. So if we account for that, if we account for the temperature changes, then we have to consider the internal energy equation. So if you go back in your notes, then the internal energy equation was something like this: del E r rho times del EI by del T plus U dot grad EI was equal to K del square T plus some deformation work done plus minus of P del dot U. And this guy was basically the sigma, the stress tensor, viscous stress tensor times the symmetric part of velocity gradient. Okay, You can go back with the double dot product. You can go back to your notes and confirm this. This was our internal energy equation. Okay, and when we have temperature changes in the flow, what we actually have to do is, so we will write, so we will make the assumptions that are usually there, that EI is essentially EI of T only. There is no volume dependence of internal energy, and this is basically we will also write it as CV times T. Okay, so we will not even entertain any changes in CV. So this CV is constant for us. Okay, we will make all the perfect gas assumptions, and we essentially get this equation. Okay, we will essentially get this equation. I don't want to rub this part, so I will. I don't want to rub this also. Yeah, okay, I can rub that. So you can form, you can do the same analysis here. You can say that there is a T that you define, and there is a T, T naught plus T prime, and so you can formulate a T star as 1 plus delta T over T naught T prime star, and you can relate the delta rho over rho naught and delta T over T naught using the thermal expansion relation, that delta rho over rho naught is sum minus alpha times delta T. Okay, this is the thermal expansion relation. Where this alpha is the thermal expansion coefficient. Okay, and from here you can replace this delta T by T naught with the epsilon and formulate the order epsilon equation for your temperature. Okay, so I will ask you to go back and do this exercise and derive the assumptions which are needed to derive the equation like this. So the equation that we get is, actually, let me do just one simplification for you, and after that you can do the derivation yourself. So this P del dot U term is actually replaced often using the ideal gas assumption. So del dot U is minus P by rho d rho by dt from continuity equation, and here what you can replace this as is, hold on, yeah, so minus P by rho d rho by dt, which you can replace as P alpha dt by dt from definition of alpha, that is 1 by rho d rho by dt is minus alpha dt by dt. Okay, you can replace this here, and the additional relation that you can use is rho Cv plus alpha P is rho Cp. This holds for ideal gases. Okay, and I will ask you to just accept it for now, that it holds for ideal gases, and we will use this irrespective of if we are dealing with ideal gases, liquids or whatever. We will just use this, and the equation that you should be able to get in T prime star should look something like this. So there should be a non-dimensional number here, and this is the equation that you will get. Okay, derive the conditions under which, so I will give you a hint. So this is actually 1 by Reynolds number times Prandtl number, and there are other terms which are actually ignored in this equation, and I will ask you to go back and derive this, derive the conditions for this to hold. The important point that I want to make here is that, Okay, this is the final equation you will get, and in a lot of textbooks in fluid mechanics, in heat transfer, you will see this equation, the momentum equation, and this continuity equation as the set of equations which describe a system where you have temperature fluctuations, and due to those temperature fluctuations you have small density fluctuations. You will see this system of equations written together. The question that you need to ask is, but this is our higher order continuity equation. If you substitute, so from here, from the definition of this T star, you can show that the dimensionless fluctuations in temperature are actually equal to minus of dimensionless fluctuations in density. You can show this, okay, using this relation, sorry, this relation together with this definition. You can show that T prime star is actually minus rho prime star, and when you substitute that here, you will see that this equation and this equation will not be the same. They will be contradictory. You will have two different equations in rho prime star, okay, and the reconciliation is the velocity due to diffusion of density. In our derivation of this equation, we have ignored that velocity, but there needs to be a diffusion velocity that you account for, which basically accounts for this diffusion of temperature or diffusion of density.
Could you repeat the last part again?
So just substitute rho prime star T prime star equals minus rho prime star here. What will you get? Just substitute T prime star equals minus rho prime star,
Extra term.
right? There will be a, the equation that you will get is del rho prime star by del T star plus this guy equals 1 by Re times PR times del star square rho prime star, and these two equations are contradictory. You have two different equations in rho prime star, okay, and the,
How are we replacing it
no, this is by def, so you can look here, okay. So this is delta T by T naught. So delta T by T naught is simply minus 1 by alpha delta rho by rho naught alpha T naught here. So this is minus epsilon by alpha T naught. So you can write that T star is 1 minus epsilon by alpha T naught T prime star, okay, and from here, and the definition of alpha, where alpha is defined using this relation again, that rho minus rho naught will be equal to alpha times 1 plus T naught minus T, right. That is the thermal expansion relation, okay, that is basic thermal expansion relation. So when you substitute that here, you will get that, let me just, so there should be a minus sign only. So T prime star is positive, then T star is smaller than 1, and so rho star should be large. So there shouldn't be a minus sign here, my bad, okay, because I have already taken that minus sign here. So when you substitute this here, so rho minus rho naught is rho prime, alpha 1 plus T naught minus T is T prime. Just a second again. There is no 1 here, right? This is rho minus rho, making these mistakes in definition. This is the definition of thermal expansion. Okay, this is how you should write it. And from here you will get that rho prime over rho naught is alpha T prime. And from there you can get this T prime star is rho prime star. Okay, and the idea is that these two equations are contradictory because we have ignored any diffusive velocity in derivation of this equation. We have ignored this Vd term in derivation here, and that Vd is important. Okay, that Vd velocity, diffusion velocity is important because it helps in reconciling these two equations, and it captures a very important physical concept that when you have a density diffusing, you do have velocity of the center of mass, which is what your u has been everywhere. This u has been velocity of the center of mass, not necessarily the translational velocity of the fluid particle. A fluid particle may have no translation, but yet its center of mass might be shifting due to changes in density, diffusion in density. Okay, so this was our whole discussion about flows with varying density and the importance of non-dimensionalizing properly, importance of choosing the right scales. If you again going back to our starting of the start of this discussion, that we chose this scale for velocity, this was important in all of this derivation. The scale of velocity that we chose was important in the derivation. Choosing correct scales is very important. Any questions so far?
So I still couldn't understand how T dash star is equal to 4 dash.
Do you understand this equation? Do you understand this equation? This is the definition, there is nothing to understand. This is how I am defining my thermal expansion. Okay. So, what is rho minus rho naught by rho naught? Rho minus rho naught is rho prime, right? That is rho prime by rho naught equals alpha t prime. What is rho prime star? Huh? Multiplied divided by delta rho. So, this rho prime by delta rho is rho prime star. What is T prime? A T prime star. So, if you substitute that here, so we saw this is okay. So, what is T prime? How can we write T prime in terms of T prime star? Okay. So, substitute this relation here. Okay, there will be a minus here. Oh, no, there won't be a minus because here I missed the minus. This was minus alpha t prime. Okay. Now, substitute this relation. Okay. Delta rho by rho naught equals minus alpha delta t. Delta rho by rho naught equals minus alpha delta t. That gives you t prime star equals rho prime star. Okay. So, this is also an important concept that of course density fluctuations and temperature fluctuations are not equal, but their dimensionless forms are equal. Why are they particularly equal? Because the density fluctuation and temperature fluctuation are linearly related. Okay, these are linearly related. So, if there is a relation between dimensional form of density fluctuation and temperature fluctuation, you will have the same relation between their characteristic scales. Basically, whatever relation you have in rho prime and t prime, you have the same relation between delta rho and delta t, which is why when you divide on both the sides with their respective scales, that relation gets cancelled out and you eventually get the identity that rho prime star is t prime star. Okay. So, dimensionless fluctuations in density and dimensionless fluctuations in temperature are equal. Does not mean the fluctuations in density and temperature are equal. Of course, they have different units, they can't be equal. So, you are eliminating those proportionality constants Here everywhere we have assumed that this alpha is constant in all of this relations.
Could you briefly explain again what you did with that, how you use that in the right
Hmm?
part of the code? You substituted then row this d dash star as row dash star.
So this part you understand?
Yeah, I
So
understand.
from here do you understand this?
Yeah.
So from here you understand this? This does
I
the same.
understood this derivation.
Okay.
Now what did you do with this? You substituted
I
this.
substituted this in this equation, which you have to confirm for me and derive the conditions when it holds. And when you substitute that, you will get this equation.
Right.
And what I wanted to show you is that these two equations are contradictory.
Yeah.
You have same equations in rho you have different equations in rho prime star.
Yeah.
And the reason why they are contradictory is because we have ignored a diffusion velocity in this. If we had accounted for that diffusion velocity, you would get the same thing here. Okay, so after this, there is just basic discussion of non-dimensionalization that I would like to just review, which is on the dynamic similarity and a different aspect why non-dimensionalization is useful in fluid mechanics, and that different aspect is in presenting your experimental data. Okay. For example, let us say you have some quantity that you are measuring. So, you have some quantity that you are measuring Q1, and you know that it is going to be a function of Q2, Q3 up to Qn. Okay. So, this quantity is going to be function of some n minus 1 quantities. Okay. Then the concept of your non-dimensionalization or pi grouping, as it is called, the Buckingham pi theorem, in all the textbooks you can find it. The idea is you may have 10 of these variables, okay, one variable here and 10 variables here. Rather than variables, let us use the word parameters, the flow parameters. Okay. So, if you do an experiment over 10 values of each of the parameters, you have 10 to the power 10 data points. If these are 10 parameters, you have 10 to the power 10 data points to report. Dimensional analysis or pi grouping usually helps you in combining those data points and making that concise, in the sense that you can replace this with some g, a different function, where this m will be smaller than n. The idea is you do not need to, for example, let us say I give you a flow which has a density, some density, the flow velocity is known, at some point the flow velocity is known, the length scale of the flow is known, and the viscosity of the fluid is known. Okay. Now I change these quantities such that, let us say the flow was in water, I change it to flow in honey, so that I change my velocity and length scale accordingly, so that this ratio remains constant. What dimensional analysis is trying to say is that you will get the same pi 1, whatever group you have formulated on the left hand side, you will get the same value of pi 1. So, experimentally there may be different setups that you have used, but physically it is the same data point. That is what this pi grouping is trying to tell us. Okay, that physically it is the same data point. For example, let us say we say that there is a sphere and you have some pressure difference across the, so this is the upstream, this is the downstream location, and you have some pressure difference between the 2 points, and due to that pressure difference you have some drag force that is acting on the sphere, and you say that okay, this drag force is going to be, the pressure difference is going to be a function of the density of the fluid, the velocity of the fluid, my diameter of the sphere, and the viscosity of the fluid as well. Okay. You make this, you say that these are the parameters on which this pressure difference depends, and when you do the non dimensionalization or this pi grouping, you will find that okay, essentially what I am trying to say is this, that the drag on this sphere or the dimensionless drag on the sphere, the dimensionless drag on the sphere is a function of this dimensionless number. Okay. And if you notice these quantities, essentially these quantities are how we decided the characteristic scales in our previous non dimensionalization of governing equation problem. Okay. So, this pi grouping also informs us what are the typical scales that you have to consider in the full differential analysis of the problem. It helps you in reporting the experimental data, making it concise, making it more physically informing. It also helps you in analyzing your governing equations in a more general fashion by eliminating this dependence. Okay, there is a flow of water, there is a flow of honey, it is happening in a pipe of diameter 1, it is 1 meter, it is happening in a pipe of diameter 1 centimeter. What are the differences? It helps you eliminate those differences, that if you are keeping these kind of dimensionless numbers or these pi groups as constant, then it does not matter. Experimentally you may use the different apparatus, but phenomena you will get the same phenomena back, you will measure the same things. Okay. And you can go back to your introductory fluid mechanics course to review this Buckingham pi theorem. So, I am not going to give a full review of it and the examples, but I will expect you to guys to be able to solve them in the exams, because it is really a very introductory concept. And if you have questions, you can always ask me. For example, the first thing that you guys should question is how many of these pi groups will be formed. Okay. The first thing that you should question is how many of these pi groups. So, here we have total of n parameters and here we have total of m pi groups. What is the relation between this n and m? Okay. You can go back to the statement of Buckingham pi theorem that if you have r independent dimensions, then m is n minus r. Okay. Have you done this? Have you done Buckingham pi theorem? You should have done this in your introductory fluid mechanics course. So, that is basically what I am doing here. Usually in this it is not written as pressure difference, it is written as this drag force. So, you will get an F by rho u square L d square as well. Okay. So, this is where I would like to stop with the non dimensionalization and dimensional analysis discussion, and I would like to use it to start the next discussion. I would like to use it to start our next discussion. So, going back to our dimensionless incompressible flow without any varying density equations, we have this. Okay. And I would like to use this to start our discussion on low Reynolds number flows, or you can think of them as you can think of them as flows where Re is much less than 1. Okay. Re is much less than 1. So, you can, those of you who are looking at this equation properly, you can quickly deduce that basically I am looking at a scenario where this term is dominating, okay, but that is not the whole story. That is not the whole story, because if you remember, then this P star I had defined as the P by P naught, and when I non dimensionalized this gradient of pressure term, okay, then there was a basically, so there is a rho u square over L that you get on the left hand side, and the whole thing, and then you get a minus P naught over L del star P star plus 1 by R e del star u star square. In this equation I have actually eliminated this P naught over rho u square, and I have taken that Euler number is 1. Okay. That is not the whole story, because in your low Reynolds number flows, so when your flows are low Reynolds number, you have viscous stresses, dominating rho u square. Basically what it means is that mu u by L is much larger than rho u square, which is basically the another way of looking at that Re is much less than 1. Okay. What does this correspond to? You can multiply the whole thing by L by mu u, and you will get that this is essentially the statement of Re much less than 1. Okay, that these scales u, L and mu, they are related with this in this fashion, that rho u square will be a very small quantity compared to mu u by L, or if you multiply this, you will get that Re is much less than 1. Okay. So, in these kind of cases, your correct pressure scale or a pressure scale, so correct pressure scale is not rho u square, but actually it is mu u by L. The correct pressure scale that you have to take is mu u by L, in which case this P naught over rho u square becomes 1 by Re.
So you just multiplied the second equation with rho u
Hmm?
square by L. There you just multiplied the second equation with rho u square by L.
So, the correct non dimensionalization of the governing equations for these low Reynolds number flows is actually del u star over del t star plus this u star dot del u star times this Reynolds number equals a minus del star p star plus 1 by Re del star square u star. Huh? Yeah, this 1 by Re shouldn't be there. You're right.
So how did you decide on that pressure scale?
Because I mean, why would pressure change in this flow? Let us say you have a flow that is happening at a very small Reynolds number. Okay, the flow is happening at a very small Reynolds number. What is the pressure? The gradient of pressure is a force per unit volume. What is this force per unit volume going to balance? Is it going to balance the left hand side or the right hand side more? Okay, because the right hand side is dominating. Your governing equations satisfy this equation. Okay, your sorry, your governing equations is the governing equation is this. So, this term has to balance out something here, and if you are saying these quantities are very small, okay, then you cannot say that this quantity, okay, this quantity is also very small, so I will just solve for this equation, because your pressure scale would be incorrect in that case. Okay, try doing this, we will see if we can solve an example of that, and we will see that you will get very nonsensical results. For example, let us say you have a very low Reynolds number flow happening between two channels. You know that there is a pressure gradient required. So, you know there is a pressure gradient in this direction required to drive the flow in this direction. Okay. What is that pressure gradient force balancing the viscous stresses from the walls? Okay. If you just ignore that pressure gradient, you will not have any viscous forces from the walls. Okay. So, the correct pressure scale in these flows, the correct pressure variation in these flows is not due to the inertia of the flow, that is rho u square, but it is due to the viscous stresses in the flow. And from there we obtain this equation, that this is del star square u star, and for low Reynolds number flows, when Re is much less than 1, let us say Re is epsilon. So, the governing equation that we get is plus epsilon, or rather minus epsilon, del u star over del t star plus okay. This is the equation that we get. Now, we are not through with this. Just here you cannot use the fact that okay, this is order 1 equation, this is order epsilon equation, because if you remember, in all of this non dimensionalization we just took any arbitrary scale for velocity as u. Okay, we just took any arbitrary scale for the length L. We did not really look at any specific pressure scales. So, in these kind of problems, to solve the equation further, what you have to say is this velocity u star is, let us say, some u naught plus epsilon u 1 plus epsilon square u 2. So, what we are saying is, due to this small Reynolds number, let us say there are some higher order corrections in the velocity, same for pressure. These are called asymptotic expansions. And then we substitute here and we will get that at order 1 the equation is at order 1 the low Reynolds number flows follow this equation. Okay. There are still two variables in this. So, we of course have another equation which you can confirm is going to remain the same, and that will be this guy. Okay. So, these are the two governing equations which we have for low Reynolds number flows at order 1. There are further higher order corrections that you can derive. There are higher order corrections that one can derive for these kind of flows, but we will in this course just bother about order 1 equations. Okay. We will just take care, we will just try to solve and see what we can get from these order 1 equations.
So when you multiplied the first equation with rho u square by
Mm-hmm.
1 by r into rho u square by will be this.
Yeah. 1 by Re is what? Mu by rho u L, no? So, mu by rho u L into rho u square by L.
It's 1 by acha.
This will be L square, you are right.
Yeah. Acha, you taken P star as a vector.
No. Yeah, this is. Okay. So, these are the governing equations for low Reynolds number flows, and we will try to see how we can simplify. As we move further in this discussion, we will solve these equations on flow past a sphere. So, let us say you have a sphere of diameter d and you have low Reynolds number flow coming onto it with some velocity u naught. We will obtain the drag relation that you guys have probably looked at in your undergraduate courses. Okay, we will derive it. We will derive the drag relation, the 6 pi mu radius into velocity is the total drag on this sphere. We will look at flows, low Reynolds number flows in channels of varying height or varying depth, as you may call, where this height or separation between the plates is a function of this coordinate. Okay, we will look at these kind of examples, and then we will move to higher. Basically, we will move to increasing Reynolds number and see what happens with increased Reynolds number.